So let's go ahead and let A1 be equal to 1, 1, 0, 0. And we'll let A2 be equal to 0, 0, negative 1, negative 1. And we'll let A3 be equal to 1, 1, 1, 1. I would like to take a linear combination of those three vectors to form a new vector B. Then, let's form a linear combination. And then this is where I would ask you, what's a linear combination, Joy? Okay, those are the operations used to form a linear combination. What is a single linear combination? Vector. If it's a single vector, and I need to have scalar vector multiplication, vector vector addition, are the scalars constant or variable? Samantha? What's a linear combination? Okay, those are the operations. So you're giving me a correct answer to a different question. So if I ask, what are the operations used to form a linear combination, what will you tell me? Okay, what is a linear combination? It's a single vector. How do I form that vector? Are the scalars in that linear combination, are they fixed or are they variable? They're fixed. So in order to form a linear combination, what do you need to tell me? A set of scalars. Throw out a set of scalars for me, Samantha. Any scalars that you'd like. Yeah, all right, great. So 2 times 0, 0, 1 plus 4 times 0, 0, negative 1, negative 1 plus 6 times 1, 1, 1, 1. Just for giggles, I mean, I guess we could do this, right? This is going to be 2, 2, 0, 0 plus 0, 0, negative 1, negative 1 plus 6, 6, 6, 6. Ooh, that's a scary vector, huh? There's 4 of them, though. There's 4 of them. Yeah, we're good. And now what? Oh, I think this is supposed to be negative 4, right? Okay, now what? What is this thing? 8, 8, 2, 2. Can you write this as a matrix vector product? We haven't defined that yet, but yeah, what would that matrix vector product be when we get there eventually? We're not there yet, but what would that be, Nick? The first vector becomes the first column, so this would be 1, 1, 0, 0. The 0, 0, negative 1, negative 1, and then what? 1, 1. And then Nick, I might ask you for your help on this. So where did the first column in my linear combination go? The first column vector? The first column of the matrix. Where did the second column go? And where did the third column go? Okay, now let's talk about rows. Where does the first scalar of my linear combination go? In the first row of my matrix X. Where does the second scalar go? Second row. And where does the third scalar go? Third row. Which means this linear combination is actually a solution to a matrix vector multiplication problem. Right? Yeah, go ahead, Emin. This is not row vector multiplication. This is another bone that I have to pick with the introductory linear algebra the way we teach it currently. So, yeah, I'll get more into this. So, formally speaking, we are not talking about matrix multiplication. I'm setting the foundation so that you can make the connection. Formally speaking, the only thing that we've defined in this math class today that's new is what? Linear combination. What's a linear combination? It's a single vector. What operations are used to form a linear combination, Blake? Underneath, however, do you remember what I said the first day when I was like, I'm going to have you memorize some stuff and then test you on it, and you're not going to understand everything that you remember? Call that the foundation of a house, right? And my claim was, if I don't do that, do you know what happens as we go through the quarter? Looks like I'm teaching you a bunch of random shit. You ever go through a math class and you're like, I don't understand how the hell this thing connects to the other thing. And then if you're lucky by the end of the quarter you make the connection. If you didn't, you're like, well, I have no idea what just happened, but whatever. Right? I got through, right? But if we start with an understanding, my claim is now we only have four problems we're going to solve in this class. Matrix vector multiplication, linear systems, least squares, and eigenvalue problem. There's two types of linear systems. How is linear combination? We're not there yet, but how is linear combination related to matrix vector multiplication? Every matrix vector multiplication problem is a linear combination, where the vectors used to form the linear combination come from the columns of the matrix, and the individual scalars used to pair off with those vectors come from the corresponding row entries of the vector that you're multiplying, and then the linear combination is the function evaluation of matrix vector multiplication. So it's a single range space element.